I share the screen.
Okay, so welcome everybody to the One World seminar. Happy and proud to have here today with us Eilon Solan from Tel Aviv University, author of the book Game Theory, together with Mashler and Zamir, associate editor of the International Journal of Game Theory, advisory editor in Games and Economic Behavior, and his main area of interest is stochastic games, quitting games, stopping games, and all sorts of stochastic games. Today he's going to talk to us about identifying the deviator. And Eilon, stage is yours.
Yeah, thank you very much. And indeed, today I'll talk about what does it mean to identify a deviator, how we do it. And this is a joint work with Eilon from Tel Aviv and from Princeton, who is here with us, with Benjamin Ganby, who is a PhD student at Cornell, Xiaoyu He, who is a postdoc at Princeton, and Eran Shmaya from Stony Brook, who is also with us. Yeah, why? Okay. So, no, 1 second. 1 second. Okay, so I will start with the motivating story, which is as follows. So Alice and Bob, we would like Alice and Bob to generate a random sequence of bits, zeros and ones. And Alice should generate the odd bits, and Bob should generate the even bits. Now, how do they generate the bits? They are supposed to generate the bits. So Alice is supposed to flip a fair coin in every odd period and to report the outcome of her coin. And similarly, Bob is supposed to flip a fair coin in each even period and report the outcome of his coin. Okay, so Alice in flips her fair coin in odd periods and Bob in even periods. Now, this way, we obtain an infinite sequence of bits. And okay, so they were supposed to flip fair coins, but how do we know that they indeed did it and did not deviate? So we decide to have a test, some randomized test. There are many randomized tests. I will not, it's not really important which test they decide to run, that I decide to run, but suppose that our test is as follows. So we check whether the long run frequencies of ones is 1/2. And if the long run frequency is 1/2, we announce that the sequence is random, and otherwise we know it is not random. Okay, so this is our randomized test. Now, suppose that we did this experiment. Alice and Bob flipped their coins. They maybe or maybe not reported truthfully the outcome of their coins, and we got an infinite sequence. And suppose that the realized sequence fails the test. So the long run frequency is not 1/2. Okay, so now with probability 1, one of them deviated, at least one of them. Who is it? Alice or Bob? So given the infinite sequence of bits, we would like to identify the deviator or deviators. Okay, so in this case, it is pretty easy, right? We look at the long run frequency of ones in Alice's sequence, of the long run frequency of ones in Bob's sequence, and whichever differs from 1/2, we know that with probability 1, that player deviated. So far, I hope everyone is with me. Suppose that now we decide to run a more elaborate test, randomized test, which is we check for each prefix of this sequence from the first bit to the kth bit. We check we count how many zeros we got and how many ones we got. If this number, those two numbers match infinitely often, then we proclaim the sequence as a random sequence. Okay, so if we think about it, that Alice and Bob essentially control a random walk. Each one is one step to the left, each zero is one step to the right. And we know that in a fair random walk, we return to the origin infinitely often. So we know that we should have infinitely many prefixes in which the number of zeros matches the number of ones. Okay, so we know that if Alice and Bob both follow the procedure we ask them to follow, then we know that the test should be passed. Suppose again that the sequence fails the test, so that our random walk returns to the origin only finitely many times. Who among Alice and Bob deviated? Can we look at the sequence, look at the zeros and ones that both generated, and identify the deviator? Now, know that this is not so easy to do. Why? Because, for example, we know that a random walk is, one could ask, okay, check whether each one of them, the distribution of bits is 1/2, 1/2. Will that do? The answer is no, because we know that a random walk stays between plus and minus square root of n, which means that if Alice chooses 1 slightly more often than 0, 1/2 plus n to the power 1/3, then the sequence will go to infinity. So the random walk will converge to infinity, but overall she chooses 1/2 of the times 1. So such a naive test wouldn't catch Alice. Also, Alice can just mimic Bob, and a part of the first bit, she can choose the minus of the bit that Bob chose, the other bit that Bob chose. So if Bob chose 1, she chooses 0 in the following period, and if Bob chooses 0, she chooses 1. So she always cancels out Bob's sequence, so, Bob's bit. So we will never get, or if the moment we went far away enough from 0, we will never get back to 0. So she's perfectly correlated with Bob, but if you look only at her sequence alone, then it is perfectly random. So it is not easy to detect here, to identify the deviator. So anyway, this is our motivating story. We have a process, flipping a coin, a fair coin. 2 players, one flips the coin in even periods, the other in odd periods. We have a target set. In our case, the target set was that the random walk returns to the origin infinitely often. Suppose that we did not reach the target set, and we would like to identify that player who deviated. So let's see the formal model. We have a finite set of players. Carl, do you have a question?
Yeah, I do have a question indeed. Can you give me some other applications, maybe in game theory, or is it really only this special example that you have in mind? I'm thinking about the bigger picture, why I should be interested in this. It's an interesting mathematical problem, but it might not, or might pertain to game theory.
Okay, so let me describe the model, and then I will talk about applications. So we have a finite set of players, I. Each player has a finite set of actions, AI. So in our case, AI was 0 and 1, the two bits, and the set of players was Alice and Bob. A is the product of the AIs. This is the set of action profiles. And N is the horizon, which can be either finite or infinite. So we will either study the finite game or the infinite repeated game. So even though I use the terminology of games, there is no game here because there is no payoff function. what is a goal? So a goal is a pair. It is a strategy profile, sigma star, which in our example was choose each bit with probability 1/2 in every period. And we have a target set D, which is a set of plays. So D is a subset of the set of all plays. And again, a to the power n, this is either the n stage problem or the infinite stage problem, depending on whether n is finite or infinite. Usually, we will think of target sets D such that the probability that they are attained under sigma star is either 1 or close to 1, as in our motivating story. A blame function, which is an important concept in this talk. This is a function from the complement of D to the set of players. So if the realized play, finite or infinite, turns out to be not in D, not in the target set, then we would like to point at the player who deviated. This is the F of the play. And we will proclaim the player F of the play as the deviator. And we say that a goal is delta testable for some positive delta if there is a blame function such that no player can, by deviating, can cause us to blame an innocent, can cause us to blame some player who is not him. So, do you see my cursor? Okay, so the goal is delta testable if for every player I and every strategy of player I, if all other players follow the sigma star, their pre-designed procedure, and only player I deviated to sigma I, then the probability that we did not reach our target set. If we reached our target set, we do not care whether you deviated or not. We all care what happens if by deviating you caused us not to reach our target. So the probability that we do not reach our target and we blame a different player than the deviator is small. Okay. So this is a delta testable goal. So one comment is that if a goal is delta testable, then it's the probability of D under the honest strategy sigma star is high, at least 1 minus 2 delta. And this is because it follows from the definition of testable, simply plug in, instead of sigma I, plug in sigma star of I. So the probability of sigma star under sigma star of the complement of D, and we do not blame Eilon, is at most delta. And also the probability that we do not reach D, but we do not blame Galit is at most delta. Since we do not blame Galit, or we do not blame Eilon, we cannot not blame both. So this means that the probability of D is at least 1 minus 2 delta. So if an event D is delta testable, then in particular, its probability, if everyone is honest, is high. Another comment is that if sigma star is pure, is a deterministic strategy that does not use randomization, then it is easy to find a deviator, right? So as soon as the set D, the target set, contains the unique play generated by sigma star, then this goal is zero testable because any deviation is immediately detected. We know who deviated. So this concept of delta testability is interesting only if our strategy profile uses randomization, and then we would like to identify deviations, and it is not clear how to identify deviations when players play randomly. So if a player should play a stationary strategy and the goal in some way measures depends on the long-run frequencies of actions, then we can run statistical tests, standard statistical tests to identify deviations. But in general, if the goal is some strange set, like the set in our motivating example, the random walk returns to the origin infinitely often, then it is not clear how to test who deviated. Questions about the model, and then I will answer about applications or some applications. Okay. So with regards to, I'm not an economist, I do not pretend to be an economist, but if we would like to pretend that we are economists, then we can think about some firm. We have our employees. Each employee has his or her task, and they should all execute their tasks in order the firm to reach some goal. Okay, to have our new product issued at a certain date. Now the strategies we assign to each player may be random because there is a lot of uncertainty about what will happen in the future. So we do not dictate deterministic strategy for each player, but some random strategy. Suppose we did not reach our goal. The firm did not meet the goal, and then we would like to know who is the cause for that, so that we can improve our plans for the future. So this is one application, one story you can think of. The other is if you think about repeated games and you would like to construct an equilibrium, and the equilibrium is for some reason should be given by a behavior strategy profile, so not a deterministic one. And this strategy, and suppose that the payoff function is general. It doesn't depend on the long-run average frequency of actions, but suppose it is just a general payoff, a general function from infinite plays to payoffs. And we have some strategy profile, and we would like to construct an equilibrium in which the equilibrium play is to follow this strategy profile. But suppose that someone deviated, we know that someone deviated, and then we would like to punish the deviator, but we have to coordinate on whom to punish. So we have to construct some function that tells us, given the play, who is the deviator, so that we can punish him or her. Okay, so this result can be used to construct equilibria in repeated games with general payoff functions. Okay. So, and this is actually the application that called for this example, for this the study, this project. Okay, it originated from the study of equilibria in general repeated games.
I have a question about the definition, if I may.
Yep.
So the goal, it's sigma star and D. So do we require that if sigma star is played, then D is reached, right?
We would like D to be reached, yes.
But it's not a requirement, so it's not.
No, it's not a requirement. We would like to reach D, that the realized play, we would like it to be in D. If it is not in D, then we are unhappy and we would like to identify the deviator, or at least we would like to blame someone because of him or her, we did not reach D.
But can it theoretically be that in a certain model, everyone plays according to that sigma star? We still don't reach D.
Yes.
Seems that in that case, I assume that's not delta testable, so it will not probably be not a good
So
example.
so if we look at the first comment, we see that if the goal is delta testable, then even if everyone is honest, with small probability, we do not reach D.
Right.
So in that case, indeed, we will blame an innocent player. Okay, everyone followed sigma star, yet we did not reach D. But this happens with a small probability.
Okay, and the second question is just a little clarification that sigma star has strategy in the classical sense. So it's basically that based on all the history till now, each player decides on the next action.
Yes, sigma star, this is so sigma star of I, the strategy of player I. This is a standard strategy, a function from histories to mixed actions.
Okay, thanks.
Okay, so let's take 2 examples just to make sure that we follow the definitions. So again, we are back to Alice and Bob. Each one should choose a bit, 0 or 1. They choose their bits alternately. Again, Alice in odd stages, A1, A2, etc., and Bob in even stages, B1, B2, etc. So B1 is the bit that Bob chooses in the second stage. Now suppose that the sigma star of Alice is as follows. In round n, she chooses the bit 1 with probability C over n, where C is some fixed small number. So she chooses 1 with a low probability that gets lower and lower as the game goes on. And similarly for Bob, Bob uses the same strategy. So he chooses 1 in period n, in period actually 2n plus 1, with probability C divided by 2n plus 1. Okay. So you see that since the sum of 1 over n is infinity, each one is supposed to choose 1 infinitely often, yet the probability that they choose 1 in 2 adjacent stages is of the order of the sum of 1 over n squared, which is small. Okay, and since C is small, this probability that they choose 2 adjacent ones is small. Suppose that the set of bad sequences, and here I define the complement of B, the set of bad sequences is all sequences where both players choose 1 in 2 adjacent stages, 2n plus 1 and 2n plus 2. So 2n plus 1, this is Alice's. Alice chooses 1, and immediately after Alice, Bob chooses 1. So if both choose 1 after the other, then this sequence is bad. And as I just said, the probability of the complement of D is of the order of C squared, which is small. If C is small, C squared is small. So this is the complement of D. Now, suppose that it happens that the realization is bad. So the bits in stages 2n plus 1 and 2n plus 2 are equal to 1. Who do we blame? So note that Bob sees Alice's bit. He knows when she chose 0 and 1. So easily he can frame her, right? He can simply choose as one bit once after she chose 1. And he can wait 1 billion stages. Choose 0 for 1 billion stages and then choose 1. And he frames her. Similarly, Alice, all Alice has to do is choose 1 always. And then eventually Bob will choose 1. Even if Bob is honest, eventually he will choose 1 because he chooses 1 infinitely often. So if Alice always chooses 1, eventually Bob will choose one stage after her. So both can cause the other one, both can cause us to reach a bad sequence. And the question is, how do we identify a deviator? So here, the idea is pretty simple, right? I mean, look at how many times Alice chose 1. If she chooses 1, roughly the amount that she was supposed to choose, then and still the realization is bad, then probably Bob is the one to blame. But if Alice chose 1 too often, then probably she is to blame. And indeed, this intuition works in this example. So, and the following is a blame function. So we denote by Kn. This is the summation of all m from 1 to n. We look at all periods in which am is 1, in which Alice chose 1, and we look at this summation, okay? Am divided by 2m plus 1. So for each period in which Alice chose 1, we add 1 over 2m plus 1. If this sum is larger than 1, then we blame Alice. So if this sum is high, it means that Alice chose 1 too often, we blame Alice. Otherwise, we blame Bob. It turns out, easy probabilistic calculations, that this is a proper blame function. And now let's look at our random walk example. In the random walk example, now suppose that Alice and Bob choose -1 and 1. So either go 1 step to the right or 1 step to the left. Again, they choose their numbers -1 or +1 alternately. And D is all the sequences in which the random walk returns to the origin infinitely often. If we did not, if our sequence, our realized sequence is not in D, then it means that we did not reach the origin infinitely often. It means that we reached the origin only finitely many times. So we can look at the tail of the sequence after the last time in which we reached the origin. So after that, so in that tail, we never reached the origin. So I rephrased my problem and set D to be all sequences for which there is a non-trivial prefix where we reached the origin. So the complement of D, the set of bad sequences, is all sequences in which we never reach the origin. Our random walk never reaches the origin. So is it clear how this D relates to the random walk example of reaching the origin infinitely often? So reaching the origin infinitely often is the same as reaching the origin once. Okay, for the purpose of testing the deviator. Okay, so I hear that I lost some of you. So anyway, forget about reaching the origin infinitely often. We take the example where we would like to reach the origin once, exactly once. If we reach at least once, we are happy. If we never reach the origin, then the sequence is bad. And then suppose that the players are supposed to play half-half, to choose bits -1 or +1 with equal probabilities. Suppose we did not reach the origin, the random walk did not reach the origin ever, never, and we would like to know who deviated. So here I can also provide you with a blame function. The blame function is much more complex than in the previous example, but nevertheless, it can be provided explicitly. And okay, so I will not. It appears here. I will not dwell on it because okay, it is some blame function. You need a bit of technical probabilistic arguments to show that indeed it works. And I hope that this slide convinces you that it is not a trivial blame function.
Question. So
Yes.
will this blame function also work if n is large but not infinite?
So if n is large, you could think about it here as D is the set of all sequences such that we return to the origin in the until stage 1 million. Okay, and suppose we didn't reach the origin after 1 million stages, a random walk should return to the origin in the first 1 million period with high probability. Suppose that this did not happen, we would like to identify the deviator. And so you can play with this blame function, but also we will see a general proof that we have a blame function.
Very nice. Okay.
So
can I ask
yes.
something?
Yes,
Why will it deviate? The deviator gets some payoff
no,
after deviation?
no, there are no payoffs. So why do you deviate? I don't know. Maybe you made a mistake. Maybe you didn't get the proper instructions and you didn't follow your sigma star of I just because you didn't get the proper instructions, and you would like to know that you didn't get the proper instructions.
Okay.
But there is no strategic aspects here.
Okay, thank you.
As I said, this model can be used to prove existence of equilibrium, and then we do have payoffs. But in this model here, we have no payoffs, no strategic considerations.
Okay, thank you.
Yeah.
To follow up the previous question, if I may, can it intuitively, if someone deviates a finite number of times, shall it be like undetectable or something like that, regardless whether it's intentionally or not?
The question is, what is the set D? If the set D, the target set, is not, I mean, if it doesn't care about finite many deviations, then we don't care whether you deviated finitely many times, because it doesn't matter for reaching the target set. But if there are two plays that differ only in finitely many actions, one is in D and one is outside D, then yes, we would like to be able to blame someone if we did not reach D.
No, but I understand. I agree. I understand and I agree. But I think just that because probabilistically, it seems like a finite number of times, it can also be with a reasonable probability, just a probabilistic deviation. So it's hard to distinguish between such deviations.
Yeah, you are absolutely correct. But we allow for a probability of T2 delta to make a mistake, right?
Yeah.
Which is fine. So all this noise goes into the 2 delta, and then I'm allowed to make a mistake even when everyone is honest.
Yes.
You should think about it as an epsilon equilibrium. In the concept of epsilon equilibrium, right, we allow for, we punish a player with low probability, even though he did not deviate. He followed this strategy. But nevertheless, we punish him because we think that he deviated.
Yeah. Basically, I think that you can define a game based on this punishment, based on this function, on this blame function, and then it's going to be an epsilon equilibrium.
Yeah, so if the payoff, if we reach D, the payoff is 1. If we do not reach D, the payoff is 0. Then indeed, this is the strategy sigma star is an epsilon a delta equilibrium. Yes.
Yes.
Or two delta equilibrium. That's true.
Yes.
Okay. So so this is the second example that we still have on the screen. It is much more involved, and you could have thought of more involved examples. For example, a two-dimensional random walk. So a two-dimensional, suppose that Alice and Bob control a two-dimensional random walk, each one of them in odd periods and even periods, and we would like the two-dimensional random walk to return to the origin. We know that a fair two-dimensional random walk returns to the origin infinitely often. So suppose that we didn't. Can we identify the deviator? So I do not have a blame function to give you for that example of a two-dimensional random walk. This is an open problem. Okay. So for some cases, we do have blame functions. For some cases, we do not have an explicit blame function. But nevertheless, what can we say? So I'm going to show you two results. One result is, suppose that the probability of D, if everyone is honest, is high. It is at least 1 minus epsilon. Then the goal is of the order of square root of epsilon testable. Okay, so so it is square root of epsilon. We have the square root also of the number of players and a constant of 2. Okay, so this is one result. And another, what happens if epsilon is 0? So if the probability of the goal is 1 when everyone is honest, then we can identify the deviator without making a mistake. So the goal is 0 testable. So those are the two results that we have. So essentially, all goals that are achieved, can be attained with high probability are testable. So that's the bottom line. We can test everything.
I have a question. How well can you test things? Because I can test also anything if epsilon is 1. The question is the square root of I epsilon. How good is that?
So if, for example, we have 2 players, right? And suppose that the probability of D, so if the probability of D is 1,
Yeah.
then I perfectly, okay, suppose that the probability of D is 99%, 0.99. So the square root of epsilon is 0.1, right? So what we have here is 2 times square root of 2 times 0.1, which is 0.4, 0.3, about 0.3. 0.3 testable, so we make a mistake with probability 70%, 30%. If the probability of D is better than 99%, it is 99.99%, then the square root of epsilon is 1%. And then the delta is 3% testable. So we make a mistake with probability 3%. Okay?
But that I understand. This is these are the formula I was just thinking about. Asking it differently, do you have an example to show that this is in some way tight? So basically, you cannot have it better testable.
No. So this is an open question whether this figure that we have here is the optimal or not. Whether the square root of epsilon is optimal or not, we do not know that. Yes, Noga.
In the first example you described, the square root epsilon is essentially what you get. The constant is not tight, but the square root epsilon behavior is there.
Yeah, this. Yeah, so this is the first example. In the second example, our blame function is worse than square root of epsilon, right, Noga? So we do not have a blame function that reaches the square root of epsilon in the second example of random walk. And we do not know whether square root of epsilon is optimal. Maybe there is a better constant than this, a better ratio than square root of epsilon. Regarding the square root of I, we know how to get it down to the natural log of I, actually log 2 of I. But whether we can do better than that, we do not know. Okay. So this is a result. It is not necessarily the result, the best result. Okay. So here we have our results. The second thing, yes.
Question: how does this relate to fault theorems in repeated games? Because theorem 2 is a bit like if D determines the payoffs. If I have something feasible and I fear the punishment, then you can construct equilibria, no? It looks related to this, no?
Yeah, but I do not know whether and how it is related to fault theorems. I do not know. Maybe there is a relation. I don't know.
Okay, because P sigma star of D equals 1 means like it's feasible to be in D somehow, and 0 testable means you can test. So if you fear to be punished, if you're not, it looks similar, no? But
yes.
Okay, this cannot be used to prove like epsilon equilibria infinitely repeated game with more and more stages are the set of feasible and individually rational payoffs, things like this.
I guess so. I guess it can be used, yeah, to prove if you take the limit of the average payoffs, then we can use this this result to prove existence of equilibrium. But we don't need this result, right? I mean, there are easy ways to prove it, but you can use this result. In fact, you can use this result to prove existence of epsilon equilibrium in repeated games with general payoff functions that are tail measurable, okay, which is more general than the limit of the averages. So you can use this result.
Okay.
Yeah. Okay. So once we have our main theorems, let's see how we prove it. How we so what I said, theorem 2 follows from theorem 1 rather easily, and the difficulty is to prove theorem 1. So let's prove theorem 1. So what would we like to do? Suppose we are given a play, an infinite play, that is not in D. Now we would like to identify the deviator. So we would like to calculate some likelihood ratio to say whether it is to look at the actions chosen by player 1, the actions chosen by player 2, and somehow calculate a likelihood ratio to tell us whether the sequence that Jerome chose, whether it is likely or unlikely to have been chosen given Jerome's strategy sigma star of Jerome. And similarly to look at the sequence of action that Galit chose and to ask whether that sequence of action that Galit chose, whether it is likely or unlikely to occur under sigma star of Galit. The problem is that to calculate a likelihood ratio, we need two hypotheses. We have the sigma star, what Galit should play, and her deviation. But we do not know her deviation. We do not know whether she deviated, and we do not know if she deviated, to which strategy she deviated. So we cannot calculate a likelihood ratio. So this idea is very nice, but impractical, or at least it is not clear how to use it. And so what we will do is as follows. So for simplicity, I will assume that the horizon is finite. Okay, but this is only for simplicity. The transition from infinite problem to finite problem is not difficult. And we are going to define an auxiliary game. An auxiliary two-player zero-sum game with imperfect monitoring. And actually, it is going to be a one-shot game. And it will be between a statistician who is supposed to identify the deviator and an adversary who is essentially the deviator. Okay, he is nature who chooses who decides to point at a player who will deviate and to provide that player with a deviating strategy. And the game goes on as follows. First, the adversary selects a player I and a strategy sigma I for that player. Then we are going to choose a realization, not we, but nature, God, a mediator, someone is going to select a realization A according to the strategy profile. All other players follow sigma star, so this is the sigma star and the minus I for some reason here, and player I deviated to sigma I. So the adversary selected a player to deviate and the deviating strategy, and then according to the new strategy profile, we select a realization. Nature selected a realization. This realization is told to the players. Now the statistician, well, if the realization is in B, the statistician wins because we did not get out of the target set. If the set A is, if the sequence, the realization A is outside B, then the statistician is called to select a player J to blame. If the statistician blames the correct player, he wins, and otherwise he loses. Okay. So this is our game. So you see that this is a game with imperfect monitoring because the statistician does not see the moves, the selections of the adversary. All the statistician observes is the realization. Okay. But this is a game. Now, this is a game. What we would like to show is that the statistician can always identify correctly the deviator, player I. Okay, so J is equal to I with high probability. So essentially, what we would like to show is that the value of this game is high, is close to 1. That this game has a value and it is close to 1. Okay, that's our goal. And if we do that, then we prove the result. So first, the game has a value. Why does the game have a value? Well, since n is finite, the set of strategies of the statistician is finite because the set of the realizations is finite. So the strategy set of the statistician is finite, and in every one-shot game in which one of the players has a finite set of actions, we have the value exists. So therefore, the value of this game exists. And the intricate point is to show that the value is close to 1. So the min-max value of this game is at least 1 minus the square root of I epsilon. This is the last step of the proof. So what I'm going to show is that the min-max value is at least 1 minus I times the square root. So I is outside the square root, of not inside the square root. This simplifies the argument, not by much, but anyway, it simplifies it. So we would like to show that the min-max value of the game is at least something. Now, to calculate the min-max value, what do we need to show? We need to show that for every selection of the adversary, the statistician has a response that is good. So we fix the moves of the adversary. So the adversary chooses for each player I a strategy, a possible strategy sigma I. This is a strategy of the adversary in the one-shot game. A player and for the player the strategy. Now we do have for each player I, we have the strategy and the deviating strategy sigma I and the honest strategy sigma star I. So we can calculate the likelihood ratio. So now we calculate for each player I the likelihood ratio of his or her actions given sigma star, given the honest strategy, and given the deviating strategy. Okay. So what is the likelihood ratio of player I given a sequence of moves? So this is the product of all overall n stages. The probability that sigma I chooses the move AIN, this is in the denominator, and in the numerator, the same product, but relative to sigma I. So this ratio is the likelihood ratio of the actions of player I between the deviating strategy sigma I and the honest strategy sigma star of I. Now we can note that if we take this likelihood ratio and we multiply it by the probability that sigma star of this A, we simply get the probability to get A under sigma star of minus I and sigma I. So for any sequence A, if we take the likelihood ratio, now what is the probability of sigma star under sigma star of A? This is simply the product of all the numerators, overall I. So if we take this product, the product for player I vanishes, disappears, cancels out, and we are left with this product for all players without player I in the numerator here times the numerator here, and therefore we get this probability. Similarly, if we take this probability of sigma star of an action profile, an action realization times two likelihood ratios, we get another probability of A given another strategy profile. And now, if we define E of J, and now the statistician is going to blame that player that has the highest likelihood ratio, which is what we would like to do in the naive approach, to blame a player with high likelihood ratio. So EJ is the set of all realizations where the statistician blames player J. And this is a subset of the realization in which J is the player with maximal likelihood ratio, because there might be realizations where two players have the same maximum ratio. And then which the statistician can blame only one of them. Okay. Now, what we know is that if all players are honest, then the probability that we blame player J is smaller than the probability that we do not reach D, that we blame anyone, which is at most epsilon. Okay. So this was our assumption, that the probability that to reach the complement is smaller. And so now, so I will move here quickly. By the Cauchy-Schwarz inequality, we can prove that the probability of EJ when player I deviates is at most squared is at most epsilon. So by Cauchy-Schwarz inequality, the probability that if player I deviates, we actually blame player J is square root of epsilon, at most square root of epsilon. So the probability to blame someone who is not player I is at most I minus 1 times the square root of epsilon. So this is the whole proof. Okay, so we prove that the min-max value is at least 1 minus I minus 1 actually times square root of epsilon. Okay. So this is the proof of the theorem. We use the min-max theorem to prove it.
Sorry, I didn't understand one thing. So the sigma I itself is not known, isn't it? Because you don't know how they deviated. So I thought there would be an additional argument here that you estimate this with like the worst case. What did I overlook?
No, so we calculate here the min-max value. To calculate the min-max value, what do we do? And since the value exists, we know that the value is equal to the min-max value. Now, to calculate the min-max value, what do? We say for every strategy of the adversary,
Oh yeah, sure.
we need to show that we have a good response. So we know the deviation.
Yes, no, I mean, you know it, you know it, and then you can best respond. Yes, thank you.
Yeah, exactly. So the trick here was to define a game, an auxiliary game where the value exists, and then we don't need to calculate the value, but the min-max value. And then we can calculate the likelihood ratio. Now you see that this is only an existence result. We know for every strategy of the adversary, we know what is our best response. But we don't know what is an epsilon optimal strategy of the statistician in this auxiliary game. And therefore, we do not know what is a good blame function. So most of my comments we already discussed during the talk. First, this result can be used to prove existence of epsilon equilibrium in repeated games with tail measurable payoffs. Second, as I said, it will be interesting to know explicit blame functions in particular cases. I provided two non-trivial blame functions, but in general, I don't know. It is interesting. Also, I mentioned about the ratio, the square root of epsilon, whether we can improve it or not, and whether we can identify the best blame function that actually achieve the best possible rate. What happens when more than one player is allowed to deviate? So we have ideas, but we don't have any explicit result about it, whether we can identify deviations by more than one player. What we do know is that suppose that 5 players deviated, then we have a blame function that blames 5 players, at least one of them will be guilty, but the other 4 may be innocent. Okay, so this is not what we want to have. We would like to actually identify the 5 deviators. We are not there yet. Also, what happens when actions are observed with some noise? We do not know whether we can extend our result to this model as well. Thank you very much. And if there are additional questions, I'm here.
Yes.
Thank you, Eilon.
Okay. I have a few questions, but first of all, let me use this opportunity to congratulate in this audience Noga Eilon for being awarded the show prize. Okay. Now, I guess that the issue of finding a blame function, yes, not just proving its existence, is a more general question about cases by which one might know that one has this type of games, yes, let's call them Martin games, I don't know which name you want to say, that you know that there exists a winning strategy, but you don't know how to compute it. So is is there a whole class that we could identify when this is difficult, not difficult? Noga, maybe you know this?
You are muted, Noga.
Yeah, I'm not. Can you repeat it again?
I say that there are many Blackwell games, let's say Martin's games, even as 0-1, that you know that you could prove that player one is a winning strategy, but and you cannot construct a winning strategy.
Right.
So is there some, I would guess that probably the logicians have been trying to trace, to coin those type of games. So is this a special case that we don't know how to find it? Is it an instance of one of these general classes of games that the statisticians claim that you cannot compute? Maybe even there are results that you cannot compute an optimal strategy.
Yeah, I don't know if there is a connection. So, for example, there are these games that we know that some player is winning because of strategy stealing, but we don't know an explicit strategy. But yeah, but I don't know if there is any connection.
Yes. Okay, and another question, Eilon, you mentioned, I think maybe I already asked it at some point, about the issue of a group of deviators.
Mm-hmm.
Yes. But if you split the players into two different groups, yes, and only one of them deviates, yes, so can you not make various blame functions for various subgroups, assuming that you know that not all of them are deviating, at least one is honest? Can you generate many such blame functions, and as a result of all of them, to identify the set of players that deviated?
So suppose that some players may deviate, but we know that at least one of them did not deviate. So what you would like to do is you would like to divide the players into a group of a single player and n-1 players.
And the complement, yes.
And the complement. And then to test whether
the player deviated or the complement.
Right.
And you do it over all players, yes.
Yeah. How? So for that you have a blame function.
Yes.
Right.
So basically you could know if there is.
But suppose that you are one of the deviators. And now I consider the set that you deviate and also someone from your complement deviated. So now we are in the setup in which both players deviate, right? You and the rest, thought of as a single player, also deviated. I do not know whether we can now, do we have a blame function that identifies that both players deviated? I don't know.
But basically, if you know that one is not deviating, yes, then and you find that the complement is deviating, okay, so you could test basically, if I understand your result, you could test also if somebody didn't deviate it. And if you make in parallel those tests on each one of the players, you know who are the deviators.
Yeah, but suppose that you deviated and Noga deviated. Suppose. And they test you and your complement.
Yes.
And suppose that now you deviated, but also Noga deviated. So your complement also deviated. Suppose that my blame function tells me that the complement deviated and you didn't. Why? Because the complement deviated, so it identifies it.
Okay.
So do I announce you as an honest person?
No. Now you know that I didn't deviate. Now you take groups.
No, but you actually did deviate. That's the issue. You did deviate, Abraham. you deviate and Noga deviated. But when I test you against everyone else, then the test tells me that everyone else deviated. Someone from the else set deviated, and you didn't deviate, right? Because our blame function only blames a single player. So it has to choose either you or the rest, because both of you deviated, but it tells the rest deviated. So
Okay,
it
so
tells
if I
me that you
didn't
didn't
deviate,
deviate.
if I didn't deviate, you blame the rest. Okay.
Mhm.
So assume that you discover that it deviated, and then you test the rest. Now you take me and Noga together against the rest.
Mhm.
So if both of us didn't deviate, then you will blame the rest.
No, so suppose that only you and Noga deviated. In that case,
No,
it
you
will tell,
already discovered that I didn't deviate by your first test.
yes, but you actually did deviate.
But
The point is that you did deviate. You deviated, Abraham. You and Noga deviated.
so you say if both have deviated, then you only require that you will blame one of them.
Exactly. We blame the one with the highest likelihood ratio. It happened to be the other guys, not you. The group that includes Noga. And suppose that indeed we do all the subgroups and we find that Noga indeed deviated. So we blame only Noga and not you. But you actually deviated.
Okay.
So I do not know whether this can or cannot be done. I hope it can.
Are there more questions? Well, if not, then we thank Eilon again.
Thank you very much.
So sorry, Alan, can I ask a question?
Yes.
So in your proof that you fixed finite end. So your model actually, so the result is true for infinite game. So is there any gap in the proof or?
So I assumed that n is finite, so that I have easily that the game has a value.
Yeah.
Because when n is finite, the value exists.
Yeah.
Suppose what happens when n is infinite. Okay, so the problem is an infinite horizon problem. In that case, it is not true, or I cannot say easily that the game has a value. I have to work a little bit to prove that the game has a value. So what we do, we say, okay, so since the probability of D is at least 1 minus epsilon, and since all probabilities over the space a to the power infinity are regular, we can approximate B from below by a closed set. So we can assume without loss of generality that the set D is closed. Now, if the set D is closed, then the payoff function in this game is upper semi-continuous. And then we can apply a fixed point theorem for upper semi-continuous functions to show that the game has a value. So we have to work a little bit harder, but it's not really an issue, a problem.
Okay, I see. Thank you. So a further question is, suppose that game is actually finite. So is it easier to construct a blame function or not?
I don't know. Noga, what do you think?
I mean, the proof you described was for finite, right?
Yeah.
I mean, I don't think there is a big difference.
Yeah. So unfortunately, the answer is no. That we are not aware of.
But you can maybe there is some algorithm for you to find the optimus value in finite game that is easier.
Yeah, if there is an algorithm, I guess there are algorithms. to find optimal strategies in zero-sum games, right? We know there are such algorithms. The only problem is that the game is quite large, right? Because the set of so if each player has 2 actions, then the set of strategy profiles in each stage is 2 to the power the number of players, and then you have to take that to the power n to see the number of realizations. So the game is quite large. So to actually run those algorithms, this might be problematic.
Okay, I see. Thank you.
Yeah, sure.
Hello, may I ask a question?
Yes.
So first, I mean, thanks for the talk. So here, I think the result is mainly focusing on the probability of detection, right?
Mm-hmm.
So do you have any idea about the probability of false alarm?
So we know that we assume that the probability, if everyone is honest, of D is at least 1 minus epsilon, which means that if I understand you correctly, the probability of false alarm is at most epsilon. Because the probability that if everyone is honest, nevertheless, the realization is not in D, this is a false alarm. Then we would say, wow, someone deviated, and the probability of false alarm is at most epsilon.
Okay. Okay. Yeah. Okay. Thanks.
Yeah, sure. More questions? So thank you very much. And Galit, we meet again in 2 weeks.
We meet again. I don't know. Let me check.
So
I don't remember by heart the schedule.
Eilon, do you have a working paper?
yes, indeed.
Yeah. No, we have no talk scheduled. I think until next year
Okay.
from now. So unless somebody wants to present.
Okay. So we do have a working paper. I can post it on the chat.
Thank you.
Yeah, sure.